Okay, so we're gonna go over some stuff from chapter 10, right? Or chapter 9. No, chapter 10. So let's start with the first one here. So this is the 10A homework. And there's only 4 questions on each assignment, I think. So hopefully it's not going to be too bad for y'all. So, do college students enjoy playing sports just as much as watching sports? The researcher randomly selected 10 college students and asked them to rate playing sports and watching sports on a scale of from 1 to 10, with 1 meaning they have no interest and 10 meaning they absolutely love it. The result of the study are shown below. So assume a normal distribution, what can be concluded using the alpha equals 0.05 level of significance. So for this study, first of all, whenever you're talking about sample means with this small of a sample, it's going to be a t-test. And these, the 2 population means depend on each other, because certainly a person that likes to play sports probably likes to watch them too. All right, so those definitely they depend on each other. So we're going to pick the t-test for the difference between 2 dependent population means. So college students enjoy playing sports just as much as watching. So in all of these, the null hypothesis is going to be the difference in the means. Mu d stands for difference in the means equals 0. And then it says, do college students enjoy playing sports just as much? So it's not really saying less than or greater than. This is a does not equals. So we'll say the difference in the means does not equal 0. All right, let's make sure all those take, we'll go through them. Okay, there we go. So we got all those right. So now the test statistic for this one, we are going to calculate the differences. So we're going to go the top one minus the bottom one. So what we're going to do is we're going to go to stat, edit, and let me clear all this business out here. So clear out your list. Remember, we go to clear, enter. So then up, I'm going to go clear, enter. Okay, so now in L1, I am actually going to calculate the difference. So I'm going to go 6 minus 7. So I'm going to put -1 in that first slot. The second one, 7 minus 6, I'm going to put 1. The third one, I'm going to do 3 minus 4 is -1. 10 minus 10 is 0. 4 minus 5, -1. 7 minus 7 is 0 again. 7 minus 9 is -2. Then I got -1, -6, and -2. So we're just doing the subtractions. The other way you could do it is you could actually list the play numbers under L1, list the watch numbers under L2, and then do L1 minus L2 and stick that into L3. I think it's easier to just subtract as we're doing it. Now the test we use for this one is just going to be the same old t-test that we did, because what we're trying to figure out is if the mean playing is different than the mean watching. All right, so here we go. I'm going to go to stat, tests, down to t-test, enter. So I'm inputting data, so I'm going to keep that. The mu0 for all of these problems is just going to be 0, because we're assuming that, the subtraction, but the mu d equals 0. That's what our null hypothesis is. Difference in the means equals 0. So mu0, 0. L1 is the list. Yep. Frequency is 1. The does not equal is the one that we want. And then go down to calculate. So there is our t value. Our test statistic is t equals -2.177. Our p value is 0.0575, it looks like. So the level of significance is 0.05, so 0.0575 is actually bigger. So p-value is bigger than the alpha, remember, that means we failed to reject the null hypothesis. We didn't get data that was way out there on the edges, so we failed to reject the null hypothesis. Okay, then all we're looking for in these ones now is the results. If you fail to reject, you're always looking for statistically insignificant. That means we don't have enough evidence to conclude that the null hypothesis is rejected. So let's see, we'll read the last two. The results are statistically insignificant, so there's statistically significant evidence to conclude that the population mean for, well, that's not what we're testing. We're testing the population mean rating for playing sports is not the same as the population mean rating for watching sports. So when you look down here, you always want to look for the insufficient evidence, statistically insignificant and insufficient evidence. And then we got them all correct. All right, so Estelle, I'm going to charge forward unless you have a question.
You are all good to continue.
Okay, let's look at number 3. 2 works the same way. 2 works the same exact way. So does 3, but 3 has a couple of extra questions on the bottom, so it might be worth going over those. Okay. Is memory ability before a meal worse than after a meal? 10 people were given memory tests before their meal and then again after their meal. Data is shown below. Higher score indicates a better memory ability. So once again, I'm going to go stat, edit. I'm going to calculate the differences in my head and put those in. So the first one, 71 minus 82, negative 11. Second one, 75 minus 74 is 1. And so on. So then negative 4, negative 7, negative 4, negative 1, negative 8, negative 2, 2, and negative 14. So when I calculate the differences, that's what I get. Now, if I get a wrong answer, I'll know I boogered it up. So let's see, for this study, once again, we're comparing means of really small samples. So it's going to be a t-test for the difference between 2 dependent population means. All right, we're talking about the same person eating and then, or getting tested before and then tested again after. So they're dependent on one another. Okay, so null hypothesis, difference in the means equals 0. Okay, so is memory ability better before a meal or after a meal? So is memory ability before a meal worse than after a meal? So that means is the difference less than 0. For the memory to be worse before a meal, the score is going to have to be lower than after a meal. So we're asking whether the difference in the means is less than 0. Okay, so then I got my data put in there. We're going to go to stat, tests, t-test again, data again. Everything is going to be exactly the same, except mu is going to be less than mu0. And then calculate, and we have a pretty high negative t-value. That indicates that data is going to be out in the tail. And that data is going to be statistically significant enough to reject the null hypothesis. So 0.0084, p-value is definitely less than alpha because the p-value is 0.01, or p-value is 0.0084 and alpha is 0.01. So it's definitely less than. So based on this, we should reject the null hypothesis. Okay, so the results are significantly significant. So there's sufficient evidence to conclude that the 10 memory scores, but we're not inferring about the 10 memory scores. We're inferring about the whole population. So the second one's not going to be correct. First and third are out because we do have statistical significance. So the fourth one, results are statistically significant at alpha is 0.01, so there's sufficient evidence to conclude that the population mean memory score before a meal is lower than the population mean memory score after a meal. So there's the winner. The p-value, we got a 0.84% chance. So this one, what you're looking for when you do these ones is once again, you're talking about population mean. All right. So if it starts talking about sample, like in the last paragraph, it starts talking about the sample of 10 people. Well, we're trying to infer something about the whole population. So it's going to be this one here, the second one. So there's a 0.84% chance that the mean memory score for the 10 people. Okay, so what am I not reading right? Oh, it is this one. Because this one talks about population mean, this one talks about sample mean. All righty. So it is that one. Okay. Level of significance. Once again, we're looking for population mean. The population mean memory score before is the same as after. And if another 10 people are given a memory test before and after, there'd be a 1% chance that we would end up falsely concluding that the population mean memory score before a meal is lower than the population mean memory score after a meal. That's the one. So the third one doesn't work because we're talking about sample mean. All righty, there it is. Got those all correct. So that's basically the way you handle this section of homework. And there's two others, they work the same exact way as those two. All righty. Estelle, we can wheel around after and get your questions too. That might be a better way to do it. Okay, let's look at 10.0b. So 10.0b is comparing sample means and seeing if there is a big enough difference to conclude there's a big enough difference, right? So does the average Presbyterian donate less than the average Catholic in church on Sundays? So we got 49 Presbyterian members. They averaged a $25 donation with a standard deviation of 13. Then we observed 47 Catholics, and they donated an average of $30 with a standard deviation of $15. So what can be concluded at the 0.10 level of significance? So this one, we're using the t-test for the difference between two independent population means, right? Being a Catholic and being Presbyterian are independent. So we're going to use that test. So this one, mu1 equals mu2, that's going to be the same thing you type for every one of these. So does the average Presbyterian donate less than the average Catholic? So if mu1 is the Presbyterian and mu2 is the Catholic, then those are what we're going to put in, mu1 less than mu2. Now my test for this one is going to be the two sample t-test. Because I mean, in theory, you think that that's what we would use for the other one, the one in the first section, but remember those were dependent on one another. So we wouldn't use that two sample t-test there. We're going to use that two sample t-test here where the two samples are independent. Okay, here we go. Stat test. So two sample t-test. Enter. We're going to enter the stats this time. We don't have a list of data. So then it asks for the mean of the first sample. So the mean of the Presbyterian donations is 25 with a standard deviation of 13. And we surveyed 49 of them. The Catholics, we had $30 donation with a standard deviation of 15. And we observed 47 of them.
Is there something else I can help with?
And then we go down and it looks like we want less than. So less than is selected already. Pooled, always just select no on pooled. I'm not sure what that means, but just leave that as no. And then I calculate. So we got a t-value of -1.742. And we got a p-value of 0.0424. So that is less than 0.1. So hit the less than or equal to. P is less than alpha, rejecting the null hypothesis. So the results are statistically significant. So it's going to be number 1 or 2 or 3, I mean. The results are statistically significant, so there's sufficient evidence to conclude that the mean donation for the 49, but we're trying to infer something about the population. The second choice is inferring something about the sample. So it's going to be the one right there. All righty. So let's check out one more of these ones. Let's see. So here we have one that has a table in it. Do we have a table down here? Oh, good, we got a table down here too. So let's do this one that's got a table in it. So this one, we actually have to enter these data values. Because they're independent, right? A retailer wants to see if a red sale sign brings in less revenue than the same sale sign in blue. The data below shows the revenue in thousands of dollars that was achieved for various days when the retailer decided to put the red sale sign up and days when the retailer decided to put the blue sale sign up. Okay, assume both populations follow a normal distribution. That allows us to use the t-test for small samples. So we're going to use a t-test for the difference between two independent population means. All righty, so the first one, the averages, the means are the same. Mu1 equals mu2. Second one, we have the means are going to be different, but red is less than blue, so mu1 is less than mu2. Now I have to enter these two data lists into the stat edit. So there we go, clear, enter right there. So we got 1.9, 2.3, 4.3, 4.7, 1.6, 2.6, 3.3, 4.1. Then the second list, 4.9, 5, 3.7, 3.1, 4.2, 4.7, 3.7, 3.2. So both lists are in there. So now what I do is I go to that 2 sample t-test. So stat test down to 2 sample t-test. And I want to use data because I input data. L1 is my first list. L2 is my second list. The frequencies are 1. You'll never have to change the frequencies or the pooled. So leave the frequencies at 1 and then pooled as no. And less than mu2, that's what we want. And down here, calculate. So we got a t-value of -1.956. And we got a p-value of 0.0372. That is less than the 0.1 level of significance, which means we have statistically significant evidence to reject the fact that the means are equal. So less than, so we're going to reject the null hypothesis. So we have statistically significant evidence to conclude that the mean revenue for the 8 days, so it's not this one, because this one, the second bubble is talking about the sample of the 8 days with the red, 8 days with the blue. And we want to know about the population. The results are statistically significant at alpha is 0.1, so there's sufficient evidence to conclude that the population mean revenue on days with the red sale signs less than the population mean revenue on days with the blue sale sign. That's what we are inferring about, is the population, so that's what we're looking for when we look at these. Right here, boom, first one's not going to be right. It talks about sample mean revenue. We want to know about the population mean revenue, so boom, it's going to be that one. Automatic. Then in the last one, you're looking for population mean is going to be in there twice. As you see, the last one talks about the sample mean near the bottom. So no, because we're inferring about the population mean, it's going to be the first one there. And lo and behold, we're correct. So that's basically how the second lesson works. Last week of the term, next week, we have 2 chapters, but I think they're both shorter than 9 or 10. All right. So that is it with that section. Let's take a look at how to do a couple problems from the third section. Because now we have a hypothesis test about difference of 2 proportions, 2 population proportions. So those ones, when you talk about test for proportions, it's going to be a Z-test this time. So we have our freshman psychology majors less likely to change their major before they graduate compared to freshman business majors. 432 out of 657. So those samples are big, which is why the Z-test comes into play. All right, the samples are big, plus it's like number times the p-value, not the probability, the proportion value is supposed to be bigger than 10, and definitely going to be bigger than 10 in both those cases. So that's why we use this Z-test for difference between 2 population proportions. So once, just like the last section, P1 equals P2 is the null hypothesis. So our freshman psychology majors less likely to change their major before they graduate compared to freshman business majors. So that's going to be a P1 less than P2. So we're going to enter the psychology majors as our first populations when we put this in, and the business major second. So here we go. We're ready to do the test. Stat tests. This one's going to be the 2-prop Z-test, because we're talking about proportions. So we use the 2-prop Z-test. Enter. So 432 out of the 657. Remember, we're putting the psychology majors first into the X1 and N1. So 432 out of 657. So number of successes, 432. Total number is 657. Number of successes for psychology majors, or business majors, excuse me, is 550 over 763. P1 less than P2, so we have the correct inequality highlighted. So then we calculate, again, negative 2.575, and this is a Z statistic. So that's way out on that tail. Negative 2.575, as evidenced by such a low p-value, 0.0050. So level of significance is 0.05. We're at 0.005, so we're less than. Therefore, we're rejecting the null hypothesis. The evidence was too far off for it to happen, so we reject the null hypothesis. It's too far off to happen unless P1 was less than P2. That's why we reject. Okay. Results are statistically significant, so there's sufficient evidence to conclude that the proportion. So it's not going to be the first one, because that's talking about the sample. It's going to be, looks like the third one. Results are statistically significant, so there's sufficient evidence to conclude that the population proportion of freshmen psychology majors who change their majors less than the population proportion. Yeah, that's what we are, that's what we're concluding. So there we have it. So that one wasn't so bad either. Okay, so there's one that looks kind of different, so let's go over that one. Well, 2 looks the same. 3 looks different, plus it's got the 3 questions at the end. So let's take a look at 3. The medical researchers comparing 2 treatments for lowering cholesterol, diet and meds. The researcher wants to see if patients who receive the recommendation to change their diet have more success lowering cholesterol compared to a prescription of meds. That means, does the diet, the proportion of the diet, is it going to be less than the proportion of the meds? A random sample, let's read that again. Researcher wants to see if the patients who receive the recommendation to change their diet have more success lowering cholesterol. I think that's greater than then. So P1 is equal to P2 is always this one. And this one, of course, is going to be that Z test for the difference between 2 population proportions. Okay, so this one, when we enter it, is going to be different. This one is going to look like it's the same test. Same test. This time for diet, let's enter diet first. So we get 337 over. This time I could try to add these in my head, or we could just put that calculation in there, because the total number that they put on the diet was these 2 added together, 337 plus 219. So I'm actually using that to make that calculation. 464 is X2, and then 464 plus 363 is that one. I got a P1 is greater than P2. This thing's worded weirdly, so we'll see if Teach got it right here. So Z equals 1.664. My p-value is 0.0481. We're rejecting a lot of null hypotheses here. So the p-value is definitely less because the alpha is 0.1. So we should reject. Let's see about all these. See if we're anchored in. Excellent. Good so far. All right. So since we're rejecting, we have statistically significant evidence about inferring the proportions are better for the diet than the drugs, right? Yep, that one. Okay, p-value, success rate for the population, blah, 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 blah. This one here is talking about the patients. Yep, that's the one we want. So the last one talks about sample, but we need to know about the population. So it's that one. And then there's a lot of words, huh? Sex rate. So this one, we're looking for population and population whenever we look at the level of significance. Okay, so this one talks about the population, the last one, so that's going to be the winner. All right, so that's all I was going to show you today. Please use office hours on Thursday if you're struggling, and yeah, there you have it. I'm going to stop sharing and stop the video.